Hello students, welcome to Sri Jayendra's Ring Zone classes. I'm your friend and mentor for coming classes with respect to physics. This is lecture number 7 of a unit Gravitation. So let's begin with today's class. In today's class we are going to discuss about the gravitational intensity and gravitational potential. So let's discuss it. First, we will be begin with the gravitational field that we call as in gravitational intensity due to point mass, a very small mass. Let's understood that a small mass m is kept over here, and I want an intensity. I want a gravitational field due to this point mass m. So what we are supposed to do is when a location where gravitational field is required, we always put up one taste mass m naught over there. When I say taste mass, we must understand that m naught is very small mass. M naught is very small mass. This is what we understood by the taste mass, that this will behave as the taste mass. This is very small mass. And when we say it's a very small mass, that means it is not having a gravitational pull that stronger that's compared to the this mass m. That's why we keep this as a very small. So what we are supposed to do is when and when or where and where we require an intensity, put up a taste mass over here, then find out the gravitational force acting on it. If I find out the gravitational force on it, it will be look like this. It's a force is equals to g multiplied by first object mass of the first object multiplied by mass of the second object, divide by square of the distance between these two. So this is equals to F is equals to g into m naught divide by r square. Now what is filled? What is filled? The filled is force divided by taste mass. It's E is equals to F by m naught, and when I say it's an E is equals to F by m naught, I could say this is E is equals to gm by r square. In vector form, this can be represented as minus of gm by r square into a unit vector r. This negative sign represents that it is attractive field. It will always attract, it could not repel. I hope this is clear. Let's find it out. The dimensional formula for the intensity of gravitational field. If I want to find out the dimensional formula, it is an F by m. Force, it's a kg meter per second square. M1 L1 T minus 2. M, it's a kg only. So this is M0 L1 T minus 2. I hope you got this. Have you? So always remember that this is the standard formula. This is the standard formula for a point mass. E is equals to g into m divided by r square. I hope this is clear. Is it clear? Is it? Do you understand this? Are you sure? Can you calculate the gravitational field due to point mass? Let's have a look. The question says that we have one mass over here, it's a 2m, a point P over here. This distance is of 2 meter. So the question says find out gravitational intensity due to shown situations. So this is our first question. It says that mass 2m is there, and you require an gravitational intensity at point P, and that point P is separated by a distance of 2 meter. So what you are supposed to do is, as you understand that this is gravitational intensity, and when we say it's a gravitational intensity, it means it is a vector quantity. When it is a vector quantity, first I will focus on the magnitude, and then I will switch to the direction. So let's write down the first formula. It's a gm by r square. In my case, mass is 2m. So I will write this, it's a G into 2m, divide by distance, it's a 2 meter, so it's a 2 square, which is equals to 4. So this is equals to Gm by 2. This is just the magnitude of the field. Now let's think about the direction. How could I find it out the direction? To find out the direction, you need to put up a taste mass at a place where you find out the direction. So put up the taste mass. Our taste mass will be the m naught. Now find out the direction of the force acting on this taste mass. So if force m naught is acting on this taste mass, then it means this force is acting on this direction. So direction of force is in negative x direction. So even the direction of electric field, direction of gravitational field, I'm sorry, will be in this direction. It's a minus of Gm by 2 I cap. I hope this is clear. Does it? Does it clear? Does it clear? Are you sure? Can you do this? Can it be done? Let's look at the second question. Let's suppose the situation is something like this. This is a mass 2m. This is mass m. A midpoint is there where gravitational intensity is required. This distance, let's call it r. Even this distance, again r. So what I'm supposed to do is, again, it's a superposition theorem. So what you need to do is you need to find out the individual magnitude first. So E1 would be equals to G multiplied by 2m divided by r square. This is first, this is second. What about the E2? This is equals to G multiplied by m divided by r square. Now let's just find out the direction and we will have some more idea, some more clarity about this. So when I write it's a 2m, put up m naught over here. So this m naught will be attracted by this 2m. So this is direction of E1. Even this m naught will be attracted by this. So this is the direction of E2. As I can say that both the directions are opposite to each other. So what I need to do is I need to subtract this. It's a E net, that should be is equals to E1 minus E2 because E1 is dominating. This is equals to 2gm by r square minus of gm by r square. So this is 2gm minus of gm, which will be the gm by r square. Its unit, it's a newton per kg. This is the magnitude. Direction, E net, as I know that E1 is dominating, so E net will be in this direction. It says a negative x direction. I hope this is clear. So do you understand this, how to calculate this? Do you? Great. Now let's continue doing this. Let's say the situation is two masses are there. This is m, this is m. This is the separation between these two masses, and this is the location where you require the gravitational field. This is a, this is a. So basically it is some kind of equilateral triangle, but it is not a complete triangle, but you required a gravitational field at point P. So the question is, find gravitational field at point P. This is the requirement. This is the requirement. You need to find out the gravitational field at point P. How will you do this? What can be done? So what I understand is that first I need to write down the numbers. It's a first, this is second. So write down the gravitational field, or I should say a magnitude of gravitational field due to first mass. It's a G into m divided by a square. Same way write down for the E2 as well. It's again G into m divided by a square. Now let's think about the direction, that what should be the direction of this fields. So if I want to find out the direction, I should put mass m naught over here, which is a taste mass. So on this m naught, this will apply a force of attraction. It is something like this. So this is the direction of E1, and even at this mass, a second mass will be attracting it towards it. So this could be represented as E2. I hope this is clear. So when I can write this, when I write this, I must understand that E net will be is equals to 2 into E into cos of theta by 2. I can write this because E1 and E2 both are same in magnitude. So this is equals to 2 multiplied by gm by a square multiplied by cos 60 by 2. And when I say it's a cos 60 by 2, it's a cos 30 degree. When it is cos 30 degree, it is root 3 by 2. This is 2 gm by a square multiplied by root of 3 by 2. This is gm by a square in negative j cap. I hope this is clear. This is the direction of E net. Have you got this? Have you? Are you sure? So do you understand this? Do you understand this completely? Are you sure? Great. Ready for one more question? Let's look at this question. Suppose this is 3m, this is 4m. They have been separated by distance r. So what they want that find distance from mass 3m at which there is no net gravitational intensity. Do you understand the question? Go through it one more time. You might get an idea. They said that find out distance from the mass 3m from this at which there is no net gravitational intensity. That means let's understood that this is the point P and this is at a distance of x. This is the location where net gravitational pull, or I should say a net gravitational field, is 0. If this is x, this must be the r minus x. Now does it possible? First thing, so if it is possible or not, that can be determined by the directions. If the directions are the same, if the gravitational field is having same direction due to both these masses, this is simply not possible, because when directions are same, you are going to add this, you are not going to subtract it. But if directions are different, then it might be possible that by subtraction you are going to manage this. Let's check the directions. So to check the directions, I must put m naught over here. Let's call this a 1, call this a second. So this m naught will be attracted towards the 3m. This is the E1. This m naught will be attracted towards this, it's an E2. Yes, so the net direction or the direction of due to both the masses are different, and when the directions are different, you can subtract it. So let's first write down the E1, that is equals to g multiplied by 3m divided by x square. Let's write down the E2, that is equals to g multiplied by 4m divided by r minus x whole square. What I want that it's an E net that should be equals to 0. E net should be equals to 0. So this is equals to E1 minus E2 equals to 0. That means it's a g into 3m divided by x square, that is equals to g multiplied by 4m divided by r minus x whole square. So this g and g has gone, this has gone. Okay, so this is 4x square, this is equals to 3 into bracket r minus x whole square. Let's take a square root on both the sides. 2x is equals to root of 3 into bracket r minus x. Do not commit a mistake to expand this. I know that you understand and you have the relations that It is a minus b whole square kind of thing. It's an a square minus 2ab plus b square plus, but do not ever do it. Always take a square root on both the sides. This will help us to get it done quickly. So this is 2x is equals to root 3r minus root 3x. So this is equals to 2x plus root 3x is equals to root of 3r. So this x will be equals to root of 3r divided by 2 plus root 3. This is the distance. This is the distance from the mass 3m at which there will be no net gravitational intensity. I hope you this is clear to you. Is it clear? Any doubts? Is there anything? Is there? No? Good. Let's now discuss about the gravitational potential due to point mass. So what is gravitational potential due to point mass? We understand that work done is equals to force into displacement. If we write this, if we write this in a differential term, it's a dw would be equals to f dot dr. Now what is the force that is acting? What is the force that is acting? We understood that it's a g into m divided by r square into dr. So this potential can be defined as it's the total work done. It's the total work done in displacing the particle from infinite to point p. This potential is the total work done in displacing the particle from infinity to point p. So this is equals to work done, that is equal. So if I find out work done, it's an integration of dw from where? From infinity to point p. It's a from infinite to point location p that is displaced at the r. This is equals to gm by r square into dr. Gm would be on the one side. It's something like this. It's a gm integration of r to the power minus of 2 into dr from infinity to location r. So this is equals to gm into bracket r to the power minus of 2 plus 1 divided by minus 2 plus 1 from infinite to r. If I put up the limits, it is the minus of g into m divided by r. The situation is something like this. Mass is here. This is point P, which is at a distance of r, and you want the potential at this point. So gravitational potential due to point mass is minus of gm by r. One very important thing is this potential is a scalar quantity. Always remember one thing, that when word potential came, when we came to a word that is potential, it is always scalar. And when we came to a word that is intensity or field, it is always vector. So fields are always vector, and potentials are always scalar. Please do remember this. Now unit of gravitational potential, we can write it as a joule per kg. This is the SI unit. We generally use a volt, yes, but we can use a joule per kg. It's a work done divided by mass. And dimensional formula of gravitational potential, the dimensional formula of gravitational potential work done, it's a kg meter square per second square. This is m1 l2 t minus 2 divide by mass, this is kg. So this is m1 l2 t minus 2 divide by mass, this and this has gone, so this is m0, no dependence on mass, into l2 into t minus 2. Yes, it's a meter square per second square if I check it dimensionally. I hope this is clear. So this is just the master formula. This is the master formula. Let's have a look. That it's a point mass, or I should say it's a gravitational potential. It's a gravitational potential due to point mass. That this mass is here, this point P is here, this is the separation R. Please do remember this formula. This is equals to V is equals to minus of G into M divided by R. This is the potential. I hope this is clear. Yes, minus to represent attractive force. Minus is there to represent the attractive force. This is the potential. This is equals to minus of gm by r. I hope this is clear. Is it clear? Is it? Are you sure? Now, what I understand is we have many formulas. We have many formulas. So let's just revise them quickly. That this is mass 1, this is mass 2, and the separation between this two is r. Then the force between this two, it's a g multiplied by mass of the first object multiplied by mass of the second object divide by square of the distance between this two. This is r square. So first, a second formula for the potential energy, that this is first mass, this is second mass, then it's an u potential energy. This is equals to minus of g into m1 into m2 divided by r. Yes, this one is the scalar. Force, it was vector. Next about the gravitational field, that this is field due to point mass m at location p, which is at a separation of r. So this could be given as, generally defined as an I, or sometimes they have defined it as an E as well, but generally it has been defined as I. That would be equals to minus of, it's a minus of or plus of, it's a g m divided by r square. This is the gravitational field due to point mass. It's a gm by r square. Again, it is a vector, so all respects that is to be supplied to vector needs to be provided to this also. It's a gravitational field. And last it's a potential. This is m, this is at location p, and this separation is r. So the potential could be written as, this is v is equals to minus of g m divided by r, and this is scalar. So these are just the summary sheet. These are just the summary sheet of all the formulas that we have used. These are just the master formulas. Yes, and due to point masses we can consider this. Yes, but always remember this, it's a g multiplied by first mass multiplied by second mass divided by square of the distance, something like that. So that every time when you recall it or when you calculate it, this will help us. Now let's get back to the potential. Let's back to the potential. We have this relation that v is equals to minus of gm by r, and this minus is representing the attractive, this is of attractive force. I hope this is clear. Is it clear? Now, do you have any doubts? Is there anything? Do you have any doubts? Is there anything? Are you sure? Are you sure? Any doubts? No? Great. Now, let's work for the questions based on this. Let's suppose two masses are there. One mass, it's a m1, which is of 4 kg. This is second mass, which is of m2, which is having a mass of 2 kg. At this point p is there, this point p is there, and this location is 2 meter, even this is 2 meter. So the question is, find out potential at point P. This is the requirement, find out the potential at point P. So what I'm supposed to do is, again the same thing, it's a law of superposition. This is first object, this is second object. I need to write down the potential due to both. Then this v1 would be is equals to minus of g m1 divided by r. This is equals to minus of g multiplied by 4 divided by 2. This is equals to minus of 2g. The v2, that would be equals to minus of g, let's say this is m1, minus of g into m2 divided by r2. This is equals to minus of g into 8 divided by this 2. This is equals to minus of 4g. Now what do you want? You want the potential at this point. it is not a vector, it is scalar, so you don't need to bother about that which would be the direction, whether it would attract, whether it would repel, or positive x, negative x, forget all that when it's a scalar. So here it's a scalar, so what I'm going to do is it's just the addition of this two. It's a vp is equals to v1 plus v2. When I say v1 plus v2, this is equals to minus of 2g, this is equals to minus of 4g. This will make it's a minus of 6g. For us, it's a joule per kg. This is potential. This is potential at point P. I hope this is clear. Is it clear? Is it? Are you sure? Are you sure? Great. Let's check the next question. The question says that, let's suppose the situation is something like this. Four masses are there: m, 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 m. The separation between them, it's an a by a. Separation between these masses are a by a. A midpoint is there at this point. This is point P, and the question says that find potential at point P. This is the requirement, that you need to find out the potential at point P. How will you do this? So what I understand is this is A, this is A, this will be the root 2A, and this is half of this. So this will be the root 2A divide by 2. I hope this is clear. So this will be A by root 2. This distance, this separation is A by root 2. And the separation of all this will be the same, so all this dimensions will be same. So what I'm supposed to do is, this is first, second, third, fourth. Potential due to first, second, third, fourth, all will be the same because the mass is same, the distance is same. G would always be the same, it's a minus of gm by, let's call it x. So v net, it's a net potential, or the total potential I should say this, it's a 4 times of v. This is equals to 4 multiplied by minus of gm divided by x. X is the separation, it's an a by root 2. This would be equals to minus of 4 root of 2 into bracket gm by a, volt or joule per kg, you can write this. Put this is potential at point P. I hope this is clear. Is it clear? Can you do this? Can you? Are you sure? Can it be done? Can it be? Can it be? Great. Let's do one more question. You have been asked that, let's suppose this is the situation, that this is the origin, this is the origin, and one of the mass has been put out over here. This is 1 meter. Next it's a 2 meter distance. Next it's a 4 meter distance. Next it's an 8 meter distance. And to the infinite. Here mass m, mass m, mass m, mass m, and infinite. So what do they want? That find potential at origin. This is the requirement. This is the requirement. You need to find out a potential at the origin. This is origin. Basically this is 0 comma 0. So what I need to do is that simply go with the relation. This is first mass, second mass, third mass, fourth mass, and onwards. So if I add this all, it's a minus of g into m divided by 1. This is minus of g into m divided by 2. This is minus of g into m divided by separation, it's a 4. Next is the minus of g into m divided by 8, and this extends to an infinite. So what I can write is this v is equals to minus of g into m into bracket 1 plus half plus 1 by 4 plus 1 by 8 and onwards. Now tell me, how will you add this? What do you think? How this can be done? How to do this? How can I? So if you look at this very carefully, then you might get an idea that take a ratio of this two, 1 and half, it's a 1 by 2. Take a ratio of this two terms, 1 by 2, 1 by 4, again 1 by 2. Take a ratio of this two, 1 by 4, 1 by 8, again 1 by 2. Take a ratio of this and next term will be 1 by 16, this 1 by 8, 1 by 16, again 1 by 2. So if I take a ratio of consecutive terms, or if I take a ratio of any two consecutive terms that is same, and when the ratio is same, this is GP. It's a geometric progression. And for GP, we have done one of the questions based on this. It is Sn is equals to A upon 1 minus R for infinite numbers. This is true for the infinite numbers. You got this? Have you? Have you got this? So this potential could be given as V is equals to minus of G into M into bracket A, which is a first term. This is 1 upon 1 minus R. R is the ratio. The ratio would be the 1 by 2. So this is equals to minus of Gm into bracket 1 upon 1 minus half. It's a half. So this will be minus of 2 Gm joule per kg. That's it. You got it. Correct. Absolutely correct. I hope this is clear. Is it clear? Are you sure? Are you sure? Any doubts up till now? Is there anything? Is there anything? Are you sure? Are you? Any doubts? Is there anything? No? Great. Let's look at this. In this, we are going to derive a relation for the gravitational field due to the ring on its axis. So we will see one of the derivation, and then we will directly come to the conclusions and the relations. So let's first have a look that if I have been asked that calculate the gravitational field intensity due to uniform ring of mass m and radius r at a distance x on the axis from the center of ring. So this is one of the ring, and on this axis at the location x from the center, I want a gravitational field at the here. This is the radius of the ring, which we call as an r. This is the perpendicular distance from the center of the ring on its axis, it's an x. So definitely this will become under root of x square plus r square. Yes, so first what I need to do is I'm going to take a smaller segment, and I will call that mass as a dm, and I will write the gravitational field for it. That could be written as dE is equals to g dm divided by r square, and that is along the direction of p2a. Yes, because it's a gravitational field and it is always attractive in nature. So when it is attractive in nature, it will be always towards the center. If I take one of the component along the p2o, something like this, that that could be written as it's a dE cos theta, and that would be equals to g dm by r square into cos theta. If I integrate that, if I integrate this, then I will be having that E is equals to integration of g dm divided by r square cos theta. It's a g cos theta, and I'm going to integrate it fully for the entire mass. If entire mass is going to be integrated, that I understand that total mass is m, and when total mass is m, it would be the gmr upon r square plus x square to the power 3 by 2 towards the center of the ring. This is the gravitational field due to ring on its axis. So this is one of the derivation of the gravitational field. If let's suppose I want to find out, if I want to find out, let's say, the gravitational potential due to ring on its axis, I can look like this. This is the ring, this is radius r, This is the distance x over which potential is required, and this is the point P. Yes, if I understand this distance as an r, the mass is m. So what I can write for the potential is that it should be is equals to V is equals to minus of G into m divided by the distance. Then the distance could be written as, it would be r, that could be written as minus of G into m divided by r, and when I put r, that is equals to root of r square plus x square. This is the potential. This is the potential on the axis of the ring due to ring. I hope this is clear. Is it clear? Is it? Are you sure? Do you understand this completely? Great. Now let's look at this. This is the summary of this. It's a gravitational potential and field due to the ring on its axis. For potential, it's a minus of gm by x, or that could be written as minus of gm divided by a square plus r square in a whole square root. Here I have taken a as the radius, and r is the perpendicular distance. And if I am supposed to plot this, it's a graph of, let's say, potential versus distance. It's a graph of potential versus distance. Then at this point, at a center, you can observe this carefully, that at the center point, at the center, this location will be equals to, it is something like this. This is minus of gm divide by under root of a square plus r square. If I put here r as a 0, because r is the perpendicular distance from the center, and at point O it was at a 0, so this will be a minus of gm by a, and as soon as I am moving from the center, it would be decreasing like this. I hope this is clear. This negative sign, is there to represent that it is attractive force in nature. I hope you understand this. Do you understand this? Do you? Great. And this is the gravitational field due to ring on its axis, that we have derived as a minus of gmr upon a square plus r square to the power 3 by 2. Yes. Now if I plot this, as you understand that on this axis, if this is centered even on this direction, axis could be created. Even on this axis can be created, so this could be on a both the way. And one more very important result is that if I want E max, then what I can do, it's a dE by dr, that would be equals to 0. Then I will find that at a location plus or minus a by root 2. Please do remember this. At a location plus or minus a by root 2, I am going to have this gravitational field as a maximum. And if in this relation I'm going to put the value of this r, what I am having is that gravitational field is equals to minus of 2 gm divided by 3 root 3 a square. Please remember this. This is very important relations. It's a minus of 2 gm divided by 3 root 3 a square. This is the E max. I hope this is clear. And that can be plotted very easily, that up to distance this, it would be look like this, and from this it will be decreasing on both the side. It's a mirror image. I hope you understand this. Do you understand this? Do you? Are you sure? Are you sure? Any doubts, any issue over this? No? Great. Now, what we understood is that when I write a gravitational field, I understand it is F divided by m naught. So even I understand that it is F is equals to m naught into E. So when a force has been asked, that particular location, and you know the gravitational field at that location, then you can easily find out the gravitational force at that location too. Please keep this in mind, because let's suppose a certain question has been asked something like this. Let's suppose a ring is there and this is its center. This is the radius r, and this is the perpendicular distance. This is x, and this is at point P. This ring has given a mass m, and this mass, let's call it as an m1. Suppose if someone asks me, that find gravitational force acting on mass m1. So let's suppose this is the requirement, that find gravitational force acting on the mass m1. So what I'm supposed to do is, it would be simply F is equals to m1 multiplied by gravitational field. So this is equals to m1 multiplied by gravitational field due to this mass m. It's a g m x divided by r square plus x square to the power 3 by 2. That's it. Newton. This is the force acting on mass m, which is mass m1, which is placed on the axis of the ring at distance x from the center. Do you understand this? Are you sure? Are you sure? Do you understand this? Great. Now, another concept. Let's have a look. First, tell me what is potential. That I mean to say, what is normal relation of potential? It's a V is equals to minus of Gm by R. This is what we call as the master relation. Yes, it's a master formula of the potential. This is V is equals to minus of Gm by R. Now, what is master formula of potential energy? I must say it's a minus of G into M into M1 divided by R. So if I observe this two formulas very carefully, what I observe is that potential energy could be written as potential V multiplied by mass m1. Do you understand this? Potential energy could be written as potential V multiplied by mass m1. Do you understand this? Are you sure? Are you sure? So do you able to use this? How we are going to use it? Let's have a look. Suppose I have been given a ring, and this is its center, this is its distance on the axis at x, this is point P, this is a radius r. I hope this is clear. So if I have been asked that, let's suppose first write down the mass of this, it's an m. Let's suppose I have been given that mass m1 is there. Initially it is at rest at point P. So the question says that find out velocity of mass m1 if it has been released from point P and reaches to the center of ring. So what I need to do is, I need to find out the velocity. I need to find out the velocity at this point. This is the center of the ring, and if let's suppose this mass m1 is there, and it is going to be released from rest, then what would be the velocity at the center? So what I'm supposed to do is that simply we are going to have an energy conservation. This is location 1, this is location 2. We used to have this approach previously as well. Total energy at 1 is equals to total energy at 2. When I say total energy, I mean it's a potential energy at 1 plus kinetic energy at 1 is equals to potential energy at 2 plus kinetic energy at 2. So this is total energy is equals to total energy. Now what is potential energy at 1? What it is? So I must write this as that potential energy at this location would be equals to potential multiplied by mass of m1 plus kinetic energy, it would be a 0. Potential energy at 2, let's call it v1. This is v2 multiplied by m1 plus kinetic energy, it's a half mv square. Now what is potential at this location? It's a minus of gm divided by root of r square plus x square. This is multiplied by m1. That should be is equals to v2. This is equals to minus of g into m divided by r multiplied by m1 plus half mv square. I hope this is clear. Is it clear? It's a m1v square. Is it clear? Yes. So from this whatever the data I am having, this is something like this. It's a minus of g m m1 divided by root of r square plus x square. That should be is equals to, it's a minus of g m m1 divided by r plus half m1 v square. This m1 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 could be gone, and I'm looking for this. It's a v square. So this is equals to minus of gm divided by root of r square plus x square. It's plus gm divided by r. That should be is equals to v square divided by 2. So this v square is equals to 2gm by r minus of 2gm divided by root of r square plus x square. And if I want a v, then I can write this in a square root. It is something like this. I hope this is clear. Is it clear? So please do understand this two approach. These are the key points to have a questions. Very important. First, it's an E is equals to F by M naught. So when and when they ask force, when they ask a force for something, and let's suppose you don't know that how to find out a gravitational force on this point, then always remembers that can I write gravitational field for this? If the answer is yes, then it would be that task has been resolved, that you just write down the gravitational field on that location and multiply it with mass m naught, and your task has been done. First thing, so this could be done, and this force can be done easily. It's an F is equals to m naught into E. I hope this is clear. And the second important concept is that when you have been asked to write potential energy, or let's suppose you required at certain situation energy conservation kind of thing. So when you need to do this, when you need to do this, you what you are supposed to do is you just write down that potential energy is equals to potential multiplied by m1. I hope this is clear. Is it clear? Is it? Are you sure? Are you sure? Do you understand this? Do you? Great. Now let's look the relation for one more thing. It is a linear mass of finite length on its axis. This is a linear mass having the finite length. This is, let's say, mass m is there, and on the axis at this point, this is the perpendicular distance, and at this point, let's suppose I want the gravitational potential and gravitational field intensity. So we are not here in a discussion of that how this has been derived and everything. Yes, this has not been written by the our NCRT textbooks. So derivation, no need to learn this, but you must remember this formulas, because this has been asked at all its various applications could be asked. So the potential would be given as it's a minus of gm divided by L. L is the length of this finite length mass into bracket sec theta naught plus tan theta naught. Or that could be, if I replace this sec theta and tan theta from this graph, I understand that it's a minus of gm by L ln L plus under root of L square plus D square divided by D. This is the gravitational potential at point P due to a linear mass of finite length. Second, let's talk about their field intensity. That could be written as E is equals to minus of Gm by LD into sine theta naught. That should be is equals to, if I replace the sine theta naught, I could write it's a Gm by D under root of L square plus D square. So this is linear mass. This is linear mass of finite length on its axis. Do you remember this? Have you? Have you remember this? Are you sure? Great. Now let's work for the uniform solid sphere for its potential and and gravitational field. So when I write the potential, this is uniform solid sphere, and when they say the word uniform solid sphere, they are considering that it's a solid sphere having uniformly mass distributed over it. So this is a solid sphere and its mass has been distributed uniformly. Let's talk about the point. Let's talk about the point where it is inside the shell. That means my distance is less than or equals to a. Then the potential could be written as it's a minus of gm by 2a cube into bracket 3a square minus r square, where I have taken a as the radius and r as the distance from center. R is the distance from the center. So this potential could be written as it's a minus of gm by 2a cube into bracket 3a square minus r square, and this gravitational field could be written as it's a minus of gmr by a cube. If I understand this formula and if I remember this formula, then I must have an idea that, let's have a look. It's a v is equals to minus of gm by 2a cube into bracket 3a square minus of r square, where a is the radius and r is the distance from the center. Let's suppose if I want the potential at the center. Let's suppose if I want the potential at the center, then potential at the center, that means r is equals to 0. And when this as a 0, when this r as a 0, this is equals to minus of gm by 2a cube multiplied by 3a square. So this a square and this a square has been removed, so I have been left with only one power of a. It's a minus of 3 by 2 gm by a. This is potential at the center of this uniform solid sphere. And if I talk about the potential at the surface at this location, then I could write that this small r could be replaced as the capital R, because this is capital A, I'm sorry, because A is the radius. It's a 3a square minus a square, it's a 2a square, and here it's a 2a cube, so this could be written as minus of gm by a. So from this I could have a very good relation that potential at center and potential at the surface could be relate, and they could be written as potential at center is equals to 3 by 2 times on the potential on the surface. Please have a look and do remember this. This is potential on the center could be written as 3 by 2 on the potential on the surface. I hope this is clear. Is it clear? Is it clear? Are you sure? Are you sure? Great. Now at the center, this is minus of 3gm by 2a that we have already derived, and at the center the gravitational field will be 0. Why? Because this is E is equals to minus of gmr by a cube. When I put at the center, this r will be 0, and if r will be 0, the E will be 0. I hope this is clear. Is it clear? Is it clear? Now this point, it's a point P outside the cell. This is the point P outside the cell. When I say it's a point P outside the cell, this is R should be, this is R should be greater than or equals to a. When I say R should be greater than or equals to a, potential would be given as V is equals to minus of gm by r, and this E, it's a gravitational field, could be written as it's a minus of gm by r square. I hope this is clear. If I'm going to plot this, let's first think for the gravitational field. For gravitational field, when it is within the sphere, that means r is less than or equals to a, this E is directly proportional to the r. So this is the point, this is the location where E is directly proportional to the r. Look at this, this is the location where we are just traveling within the sphere. Yes. Now once you are moving outside the sphere, it is E is equals to minus of gm by r square. So as soon as as soon as distance is increasing, your field is decreasing, and it has been shown by this graph. Is it clear? Is it clear? Is it? Are you sure? Great. Now let's talk about the potential graph. That potential, this is the center, potential at the center, it would be a minus of 3 by 2 gm by a, and potential on the surface, that is equals to minus of gm by a. So it would be a something like this. Once you are traveling outside the center, outside the sphere, it is something like this. It's a minus of gm by r. I hope you are clear with this. Are you clear with this? Are you? Are you done? Have you any doubts up till now? Is there anything? Is there anything? Are you sure? Are you sure? Great. Now let's look at this. This is the second situation where you are not having, when you are not having the uniform solid sphere, but you are having a uniform thin spherical shell. This shell is, let's having a mass of m, and it is having a radius of a. So a is the radius. Again, we are using the same notifications that we have used. It's an a is the radius and r is the distance. Yes. So let's look at this. It's a point P with, when it is an inside the shell, when it is an inside the shell, this V could be written as minus of gm by a, while a is the radius. Please do remember this. When you are going to use a thin spherical shell, your potential would be equals to minus of gm by a, whatever could be the distance when you are talking about the inside the spherical shell. So you must remember this, whatever the distance we are using, whatever the distance we are using, but we must use a complete radius. Please remember it. Yes. And the gravitational field will be zero inside it. Inside it, gravitational field will be zero. When I'm talking about the point P outside the shell, when I'm talking about the point P outside the shell, then this potential could be written as minus of gm by r, and gravitational field will be equals to minus of gm by r square. So let's just plot this. Suppose first plot, I'm going to plot the potential. Then when I am up to the surface, from the center to the surface, the value will be fixed. It's a minus of gm by a, so it's a straight line. And as soon as I'm leaving the surface and I'm moving outside, it's a minus of gm by r. So as r is increasing, this v is decreasing. I hope this is clear. As r is increasing, this v is decreasing. Is it clear? Is it clear? Great. Now on a second point, when point P is inside the shell, when point P is inside the cell, when it is inside the shell, this gravitational field, this gravitational field could be written as it is zero. So there is no mark over here, it's a zero. And when you are living outside the sphere, outside the shell, sorry, it would be equals to minus of gm by r square. I hope this is clear. Is it clear? Is it? Are you sure? Are you sure? Are you? Great. Now one more thing I want to specify is that the same relations will be available for the hollow sphere also. So whether it would be an hollow sphere or whether it would be a uniform thin spherical shell, the relations will be this equal. I hope this is clear. Is it clear? Is it? Are you sure? So let's just summarize this. That let's suppose this is the object, and this is let's say it's a thin spherical shell or hollow sphere. So let's suppose this is mass m, this is radius r. So if I write this on the, if I write this, let's suppose that outside on the surface and inside. Yes. So let's first talk about the potentials. Let's first talk about the potentials. So if a thin spherical shell or hollow sphere is there, then on the outside it is equals to V is equals to minus of Gm by R. On the surface it is equals to V is equals to minus of Gm by R. And on the inside, this is, as we have used the radius as R, on the inside it's a V is equals to minus of Gm by R. Is it clear? Is it clear? Great. Now let's talk about the different another object. This is a solid sphere having mass m, radius r, and this is of solid sphere. When I say solid sphere, a mass has been filled in this. When I talk about the potential outside, then this could be written as minus of Gm by r. On the surface, this is V is equals to minus of Gm by r. On the inside, this is equals to V is equals to minus of Gm by 2r cube into bracket 3r square minus r square. I hope this is clear. Is it clear? Is it? Are you sure? Are you sure? Great. So, do you understand this? Do you understand this? This is outside, this is on the surface, and this is inside. So what you need to be careful is about that. Look at this outside, both the relations are equal. For this surface, these two relations are equal, only the difference has been created over this. Do you understand this? Only the difference is at these two locations. Other than this, other than this, all the relations are the same. This is about the potential. Now let's discuss the same thing about the gravitational field. What about the gravitational field? It is about the gravitational field. First, let's take an object that this is hollow sphere. This is hollow sphere or thin spherical shell. So what would be the situation? Let's talk it that this is outside, this is inside. Sorry, this is first is the outside, then let's talk about the surface, and then it is inside. So let's call this a mass m and radius r. So when it is outside, what I can write is that it is simply the V is equals to sorry, gravitational field E is equals to minus of G m by r square. This minus represents the gravitational field, that it is attractive in nature. It's a minus of Gm by r square. On the surface, it's a minus of G into m divided by r square. And when it is inside, this is hollow sphere, so this gravitational field will be 0. This is about the hollow sphere. Now let's talk about the solid sphere. Let's say this is having mass m and this is having radius r. This is a solid sphere. This is a solid sphere having radius r and mass m. When you are talking about the outside, this is going to be written as E is equals to minus of Gm by r square. When you are talking about on the surface, it's a E is equals to minus of Gm by r square. And we are talking about the inside, this will be equals to E is equals to minus of Gmr divided by r cube. I hope this is clear. So this is the situation when it is an inside and outside. So again let's observe this, that this outside field is same on both the sides. It's a minus of Gm by r square, whether it would be an hollow sphere or whether it would be an solid sphere. On the surface, the relations are same. E is equals to minus of Gm by r square minus of Gm by r square. Only the inside would be a variable, that for the hollow sphere, it inside it's a 0. And for the solid sphere, that would be E is equals to minus of GMR divided by R cube. I hope this is clear. Is it clear? Is it? So do you understand this? Please note it down, this all relations. Please note it down, this all relations. This will help us. Please noted it. Have you noted it down? Have you? Okay. Please note it down, the relations of the potentials. Have you got this? Have you? Are you sure? Are you sure? So now, can we switch to the numericals based on this? Let's have a look. The question says, suppose the situation is something like this. Let's have a look. That this is the center. One object is of m1 mass, another object is of m2 mass. While m1 mass object is solid sphere. So this is m1 is the mass of this solid sphere, and first object is of solid sphere. And the second object m2, it's a hollow sphere. I hope this is clear. And let's put m3 at the center. Let's put m3 at the center. And what I understand is this is the r1, this is the r2. What I need to do is I need to find out a potential first. This is location A, this is location B, this is location C. Yes, so the question is find out gravitational field at A, B and C. You need to find out the gravitational field at location A, at location B, at location C. And I must write it's an m3 is the point mass. I hope this is clear. So what I'm supposed to do is, first let's take any one of the point. Let's suppose I'm going to write the gravitational field at location A. So what I'm going to understand is this A is the distance from the center. What would be the gravitational field due to this point mass at location A? First I need to consider that only. Then I understand that for a point mass it is minus of G m3 divided by A square. Great. Now next at point A I need to write down the gravitational field due to mass m1. So now I need to understand that what is m1. It's a solid sphere. So do we have gravitational field due to solid sphere when point is lying inside? Do we have this? Do we? So my answer should be yes, it would be there. Now what would be its value? Its value would be minus of G into m1 multiplied by distance. This distance is A. Divide by this is r1 square. Yes, it's a minus of gmr by r cube, where r is the distance. In this case my distance is A, so I'm going to write this. Now you have done for the m1. Now let's write down for the m2 mass. What is m2? It's an hollow sphere. For the hollow sphere, this point A is lying inside the sphere, and as this point is lying inside this m2 sphere, gravitational field would be 0 due to this, so it would be a 0. I hope this is clear. Is it clear? Is it? So can you write this? Let's write down this very quickly. It's an gravitational field at point B. Now this is the location. Again do the same thing, write down the field due to everyone and each one. This would be is equals to minus of G into m3 divided by B square. This B is outside the m1. When you are going to write down this field for the m1 by the m1, sorry, this point B is lying outside the m1, and when point is lying outside it, it's a minus of G m1 divided by, square of the distance, it's a b square. Now for this point B is lying inside this M2, this point B is lying inside the M2, so this will be a 0. I hope this is clear. Is it clear? Is it? Are you sure? Great. Now, gravitational field at point C, what it would be? As you understand that this point for the M3 mass, it's equals to minus of G M3 divide by C square. Gravitational field at point C, it's a minus of G into M3 divided by C square. Let's write down it. Let's write down it for the mass M1. What it would be? What it would be? For the mass M1, this is minus of G M1 divided by C square. Now let's write it down for the mass M2. This is, even this at this point it is outside the sphere. So this should be written as it's a minus of G into M2 divided by C square. This is the gravitational field at point C. This is the gravitational field at point C. I hope this is clear. Is it clear? Is it? Are you sure? Do you understand this completely? Have you? Have you understood this? Are you sure? Great. So ready for one more question based on potential. This is about the gravitational field. Now let's write it down. A same thing for the potential as well. Let me draw this. That this is the first object and this is the second object and this is the center. So let's call this as a first object M1, second object having mass M2, and the central body, it's a point mass having mass M3. So first object having mass M1 is the solid sphere. Our second object having mass M2, it's a hollow sphere. This is hollow sphere. And the third having mass M3, it's a point mass. What you need to do, that this is the radius, let's call it R1. This radius is R2. You need to find out the gravitational potential at this locations. Let me redraw this. It's an, yes, this is A, this distance is B, and this distance it is at C. So what you need to do is you need to find out the potential. Find potential at point A, B and C. This is the potential. You need to find out this. It's a potential at point A, B and C. How will you do this? So when I need to find out a potential at point A, B and C, let's take any one of the point and start doing it. It's a, let's call it potential at A. So what I need to do is I need to write down the potential due to each one, everyone. When I write the potential due to M3, this will be equals to minus of G into M3 divided by A. When I write the potential due to M1, please do understand this, that this mass M1 is there and this point A is lying inside the, this point A is lying inside the mass M1. And when it is lying inside the mass M1, what I need to do is it's a minus of G into M1 divide by its radius. The radius of the mass M1, it's an R1, so it's a minus of G M1 by R1. Minus of, now let's write it down for the mass M2. Again for mass M2, this point A is lying inside the sphere, so this would be written as it's a minus of G M2 divided by R2. I hope this is clear. When point A is lying inside the sphere, you are going to use the complete radius. Do you understand this? Have you? Great. Now let's write it down the potential at point B. Let's write it down the potential at point B. When I write down the potential at point B, this will be, this is mass M3, this is point B. This is equals to minus of G M3 by B. This is M1, this is B. It's a minus of G M1 divided by B. and 4 point mass m2, 4 mass m2, this point is lying within the sphere, so this will be written as it's a minus of gm2 divided by r2. I hope this is clear. Is it clear? Is it? Are you sure? Great. Now let's write down the potential at C. Let's write down the potential at C. This point is lying outside the sphere. This is equals to minus of G into M3 divided by C. This point, it's a minus of G into M1 divided by C. This is the minus of G into M2 divided by C. This is potential at C. So this all are the potentials. Potential at A, B and C. That's it. You did it. Great job. I hope this is clear. Is it clear? Is it clear? Are you sure? Can you do this? Can you do this? Yes? Great. Now let's do some more questions based on this concepts. Let's suppose a thin spherical shell is there, and this thin spherical shell is having mass m and it is having radius r. Now we have put mass m1 over here, which is at a distance of small r. So the question is find out force acting on mass m1 due to thin spherical shell having mass m and radius r. How will you do this? What can be done? What can be done? What do you think? So exactly, I don't know the formula for the force, but what I know is that at this point I understand the formula of the gravitational field. So what I'm going to do is that it would be simply the gravitational field will be equals to F divided by m1. So this force could be written as gravitational field multiplied by mass m1. But when point is inside the shell, the gravitational field will be a 0 and thus force would be 0 because E inside is equals to 0. I hope you understand this. Do you understand this? Have you? Have you understand this? Are you sure? Great. So shall I add something? Shall I? You have been asked that find out potential energy of shown system. You need to write down the potential energy. So what I'm supposed to do is that I understand that potential energy U could be written as it's a V multiplied by m1. Now I need to write down the potential due to this mass. It's a mass of a spherical shell. That could be when the point is inside, you need to use a complete radius. It's a minus of G into m divided by r multiplied by m1. So this is the potential that is equals to minus of G m divided by r multiplied by m1. I hope this is clear. Is it clear? Is it? Do you understand this? Are you sure? Any doubts, any concern over this? Is there anything? Do you understand it completely? Have you? Have you understand this? Great. Now let's move on to the next point. This will represent as the relation between gravitational field and gravitational potential. So when I derive this, it is basically the work done by an external agent to move a unit mass from a point to another point in the direction of the field E slowly. That's why, because it should not produce any acceleration through an infinitesimal distance dr. So It's basically a work done, and when it is a work done, it should be enforced by the external agent multiplied by distance moved. It's a minus of E dot dr. So basically this is dv is equals to minus of E dr, or I should say it's a E is equals to minus of dv by dr, and this dv by dr is said as the negative gradient of the potential. Yes, so gravitational field at any point is equals to the negative gradient of potential at that point. Even from this relation I can have this relation too, that E is equals to minus of dv by dr is given. I am having this relation that dv is equals to minus of E dr. If I integrate this on both the sides, at this side I am having a potential difference delta V, that would be equals to minus of E dot dr. I hope this is clear. So basically now in this situation I am having 2 points. First, it's an E is equals to minus of dv by dr. First is the E is equals to minus of dv by dr, and the second is delta V, which is equals to minus of integration of E dot dr. I hope this is clear. Is it is it clear? Are you sure? Are you sure? So we have two relations basically. This is the first, this is the second. In reality, this all relations has been derived for the electrostates that we learn in class 12. But in a competitive examinations, even they ask is for the gravitational also. So we are going to use this. Let's practice this and the things will be ours. So let's have a look at this. Let's suppose the question says that if gravitational field is given as E is equals to 4xi plus 4yj cap, it's Newton per kg. Find out potential at 2 comma 2 if potential at origin is assumed to be 0. So this is the requirement. What I am supposed to ask is that I have been given the gravitational field, and that gravitational field is 4xi plus 4yj. I have been asked the potential, and I understand that to write down the potential, what I want, it's a delta V is equals to minus of E dot dr. So when I required this dr, always do understand that when and when you write, or when and when you require this dr, you need to simply write this dr is equals to, this is equals to dxi cap plus dyj cap. To write down this, it's a delta V, this is equals to minus of E, which is equals to 4xi plus 4yj cap dot, it's a dxi cap plus dyj cap. So this is equals to minus of it's a 4x dx plus integration of 4y dy. I hope this is clear. Now what is to be limits of this? Let's look at this. They say that potential at the origin is 0. So when I write this delta V, it's a Vf minus Vi, and this is 0. So origin is at 0. So this is to be integrated. This is x, this is y. So this is to be integrated from 0 to 2. Even this is to be integrated from 0 to 2. I hope this is clear. So let's do it. It's a Vf minus of Vi, while Vi would be 0. This is equals to minus of integration of 4x dx from 0 to 2 plus integration of 4y dy integrating from 0 to 2. This is equals to minus of 4 into x square by 2. This is from 0 to 2 plus 4 into y square by 2 from 0 to 2. So this will be equals to, this is 2, this is 2. This is equals to minus of 2 into x square plus this is 2, this is equals to 2 into y square, and this is to be integrated from 0 to 2, 0 to 2. This is equals to minus of 2 into x square, it's a 4, plus 2 into y square, it's a 2, 2s are 4. So this is equals to 2 4s are 8, 2 4s are 8. This is 8 plus 8, 16. This is equals to minus of 16. It's a minus of 16. I could say that it is the 16 units. I hope this is clear. As this is 0, this is the final potential, or I should say it's a gravitational potential, basically work done divided by mass. You can use the unit joule per kg. It's a kg. I hope this is clear. Is it clear? Can you do this? Are you sure? Can it be done by you guys? Are you sure? Great. Now let's work it. Let's work it for the gravitational field. Let's suppose the data has been given that gravitational potential in a region is given as V is equals to, let's say it's a xy plus yz plus zx. It's a joule per kg. Find out gravitational field. Find out gravitational field at 1 comma 1 comma 1. How will you do this? So let's first write down the relation and we will having a certain idea. This is E is equals to minus of dv by dx, but the problem is that this is potential, which is a scalar one. So when I write anything about the potential, I don't bother that whether it would be in x direction or whether it would be in y direction or whether it would be in z direction. No, that is not our issue. But when I write this for the gravitational field, I must taken into considerations the directions as well. So what I need to do is what we call it as a partial differentiation, that I need to write then for the Ex, this is equals to minus of del V by del X. So the thing is, when I differentiate it with respect to X, I understand that Y and Z is constant for me. Same way I'm going to write this for the Ey, that is equals to minus of del V by del Y. Same way for the Ez, which is equals to minus of del V by del Z. Once I have done this, I have written Ex, Ey and Ez. Once I have written Ex, Ey and Ez, I can write this gravitational field would be equals to root of, this is Ex square plus Ey square plus Ez square. I hope this is clear. Is it clear? Is it clear? Are you sure? Do you understand this? Do you understand this? So let's just do it, and this can be done very easily. Let's have a look. So the potential I have been given, it's an xy plus yz plus zx. It's a joule per kg, and I need to write down first Ex, that is equals to minus of del V by del X at 1 comma 1 comma 1. This is required at 1 comma 1 comma 1. This is equals to minus of del by del X of potential. That potential could be given as it's an xy plus yz plus zx. So this could be written as, this is del by del X. When you are differentiating it with respect to X, Y is constant for us. So it's a del by del X of X. So it is 1. so it's a minus of y, plus del by del x of y and z. These two are the constant at this situation because you are differentiating it with respect to x, so this is 0. This is del by del x of z into x, so del by del x of x, this is just the z. Now let's just keep the value of 1 comma 1 comma 1, it is y, so it's a minus of 1 plus 0, z, it's a plus 1. So this is equals to minus of 2, this is equals to minus of 2, which is Newton per kg. I hope this is clear. Is it clear? Great. Now let's write it down for the EY, which is equals to minus of del V by del Y. This is equals to minus of del by del Y of xy plus yz plus zx. So when I differentiating it with respect to y, this y is constant, only I have been left with the x. Differentiating it with respect to y, it's a yz, it's a plus of z. It's a z and x, both are the constant because differentiating it with respect to y, this is 0. So this is equals to minus of 1 plus 0, and this is equals to minus of 2 Newton per kg. Let's find it out for the Ez as well. That Ez, that should be is equals to minus of del V by del Z. This is equals to minus of del by del Z of, it's an xy plus yz plus zx. When I write this, this is equals to del by del z, and this is x and y, both are constant, so it's a minus of 0. Del by del z of yz, this is del by del z of z, which is equals to 1. I need to write it as a y. Del by del z of z into x, del by del z, it's a 1, and I have been right, it's an x. So this is equals to minus of 0 plus 2, 1 plus 1, basically it's a 2, or I should say minus of 2. So in when I find out the magnitude of this, its vector form will be equals to, vector form of this will be equals to minus of 2 I cap minus of 2 j cap minus of 2 k cap. This is the gravitational field of this. This is E is equals to minus of 2i minus of 2j minus of 2k, and the magnitude of field is, this is equals to root of, it's a 2 square plus 2 square plus 2 square. So this is equals to, this is 2 square, it's a 4 plus 4 plus 4, 4 plus 4 8, 8 plus 4, it's a root of 12. While I say root of 12, this should be written as 4 into 3, this is equals to 2 root 3 Newton per kg. I hope this is clear. This is the magnitude of gravitational field. I hope this is clear. So can you do this? Can you? Great. So let's just wind it up this session over here. This is all about the gravitational field and gravitational potential. As it is a very detailed topic, we have covered all those aspects which have been generally asked in the gravitational point of view. So practice this kind of questions. This will help us a lot, not only in the gravitation, but it will also help us to do the questions in the electric charge and fields, which is the first unit of class 12. I hope this is clear. Please practice a lot. Only practice can save us. Thank you. Have a good day. Take care.